Okay, in the previous module I introduced you the approximation methods used in the quantum mechanics, and I talked about the need of the approximation methods in quantum mechanics, why it is required, and I said you that whenever you have multi electron atoms or molecules, small molecules, then the solution of the Schrodinger wave equation is analytical solution of Schrodinger wave equation is not feasible. And if it is not feasible, then we need some way or some means of finding out the eigenfunctions and eigenvalues. These are approximation methods are the ways of finding out the eigenfunction and eigenvalues of those systems for which an analytical solution of Schrodinger wave equation is not feasible. This I talked about yesterday. And I said you that there are two different kinds of approximation methods. One is variation methods and another is perturbation method. And I started talking about variation methods, and I said you that in variation methods, we guess a trial function and then we find out the energy corresponding to the trial function, and we guess a trial function such that it involves a variation parameter, and by minimizing the energy corresponding to this trial function, we get the value of variation parameter, and thus we get the eigenfunction also and the minimum possible eigenvalues. The basic premise of variation theorem is that any trial function, the energy obtained from any trial function is always greater than the ground state energy of the system, because whatever you are guessing is a trial function, it's not the exact function, and we try to go from this trial function to the as minimum energy as possible and more as closer to the ground state energy as possible from this trial function. And for that, what we do, if the function is proportional to the variation parameter, then energy is also proportional to variation parameter. So first we find out the energy expectation value of the energy, and then we differentiate this expectation value of energy with respect to the variation parameter, and we minimize this function, and we find out the value of variation parameter for the minima. And this variation parameter value, when we put into the function, that is the function for the minimum possible energy of the system, and the energy corresponding to this should be as close to the ground state energy as possible. This I talked about. This was the basic premise, and then I started applying the variation method for an example of hydrogen atom. Okay, and if you remember, because I left you, it is the lengthy derivation, and I left you in between the derivation. So a quick recap of what we did in the previous module is required. The trial function which we assumed was phi is equal to exponential minus CR. Obviously, exponential minus CR means C is the variation parameter. Okay, and then I said you that the Hamiltonian for the hydrogen atom, which you can write, is minus h cross square divided by 2 my del square minus E square by R. E square by R is the potential energy. Okay, so that we can write. Now, since the electron in a hydrogen atom, energy of an electron in the hydrogen atom is dependent on only on R function, it is independent of theta and function. So the Laplacian which we take here is the only R function, not theta and phi functions. So I started taking this Laplacian for the Hamiltonian, and then we wrote with the help of this trial function exponential minus CR, we wrote this equation. It's h phi is equal to E phi. So where minus h cross square divided by 2 mu del square minus E square by R phi is equal to E phi, and this minus h cross square divided by 2 mu del square phi minus E square by R phi is equal to E phi. It's the same thing. So the first thing which we did is we tried to find out the value of del square phi, and this del square phi in spherical polar coordinates is 1 by R square del by del R, R square del by del R into phi, and phi is exponential minus CR. So what we write here, del square phi is equal to 1 by R square del d by dr, R square d by dr exponential minus CR. Okay, when you differentiate this, what you get is C, you can be C minus CR. So after differentiation, we can write minus C divided by R square d by dr, R square exponential minus CR. Okay, And if you differentiate this one, you see it's d by dr of r square d by dr. So the first differential we did, and after doing the first differential, you get this one. Okay, because minus c you will get, so minus c will be here outside this differential, and then you have two terms r square and exponential minus cr. So differentiating this will give you 2r exponential minus cr minus cr square exponential minus cr. Okay, and if you take e exponential minus cr outside this bracket, then you can write minus c divided by r square exponential minus cr 2r minus cr square, and then you can multiply by 1 by r square, and if you multiply it by 1 by r square, what you get is and you bring this c also inside, then what you get is 2c minus 2c divided by r plus c square. So finally your del square psi Laplacian operator when operated on the trial function phi gives you exponential minus cr c square minus 2c divided by r. Okay, and if you look write the Hamiltonian, then the Hamiltonian was minus h cross square divided by 2 mu del square phi minus c square by r phi is equal to e phi. And this value, since it is known to you, we have calculated earlier, so we just put this value minus h square divided by 2 mu, and this was the value for del square phi which we derived earlier. So we got this equation, h phi is equal to this part. Okay, of course is equal to e phi you can write, h phi is equal to e phi, but the value of h phi is now this one. Okay, now you know that whenever you find a expectation value of a system, what do you write? You write the Hamiltonian operator, then psi d tau from minus infinity to plus infinity divided by minus infinity to plus infinity psi star psi d tau. Okay, so for any normalized function we can neglect the denominator, and if it is not normalized, then you will have to calculate the denominator also, only numerator will not do. So what we do then, after calculating h phi is equal to this one, we go for the normalization of the trial function, and for normalization what we do, and we multiply it by n, so it will be n square phi star phi, and the volume element will be 4 pi r square dr, that you know. Why 4 pi r square? Because if you go for the hydrogen atom radial distribution function, there we did it. Okay, so the volume element is this one, 4 pi r square dr, and if you normalize this one, your function was, remember your trial function was exponential minus cr, so it will be exponential minus 2 cr 4 pi r square dr, and 4 pi will come outside. What the integral will be from 0 to infinity r square exponential minus 2 cr dr. This integral you will have to do, and for doing this integral, okay, r square 4 pi r square exponential minus 2 cr dr, you can do it integration by part, or you can use the standard integral. Throughout this course I have used the standard integral. So the standard integral is this one, x raised to the power n exponential minus ax dx. This you get in any mathematics book or in any quantum chemistry books also. A list of standard integral is given. So we use that standard integral, and what we obtained is the value is 1 by 4c cube. Okay, so if you get this value, then your normalization constant is root under c cube divided by pi. What does it mean? It means the normalized trial function we can write as phi n is equal to root under c cube pi exponential minus cr. Okay, so now what you can do, your del square phi was with the unnormalized function. With the unnormalized function, del square phi we calculated earlier. You see, I will show you the by going to this one. This was obtained by using unnormalized trial function. And now when you use the normalized trial function, What do you get? Del square phi n is actually c cube divided by pi exponential minus cr c square, this one. Okay. So now h phi n with the normalized function is this value, c cube divided by pi raised to the power 1 by 2 exponential minus cr minus h cross square divided by 2 mu c square minus 2c divided by r minus c square by. It's the same equation you obtained earlier, minus this one, except the normalization factor which is added. Okay. So we add the normalization function. We added the normalization function. Energy with this normalized wave functions can be calculated using Rayleigh ratio. Then the denominator will be equal to 1. So I said you that in the Rayleigh ratio you have psi star psi d tau, and which is equal to 1 if you use the normalized wave functions. So normally I've written, what you write energy you write psi star h psi d tau from 0 to infinity. This is the numerator of the Rayleigh ratio. So what you want to write? You write this as phi n, you write this as h, you write this as phi n, and your volume element d tau is actually 4 pi r square dr. Okay. So this is what I have written here. This is the numerator of the Rayleigh ratio, which will give you the expectation value of the energy. So let's find out this integral, and you already have h phi n. H phi n is known to you. So simply put h phi n values in this integral. H phi n value if you put, okay, what do you get? You get the c cube divided by pi raised to 1 by 2 exponential minus cr. Then c cube, this is your phi n. Up to this it was phi n, and beyond this it is h phi n. From here to here it is h phi n, which is on the previous slide. Okay, it's h phi n. Okay, so you have this one, and if you solve this integral, what do? You have 4 pi, you have c cube divided by pi raised to the power 1 by 2 raised to the power 1 by 2. So bring it outside, 4 pi c cube divided by pi. Then exponential minus cr you have here also, exponential minus cr you have here also. So it will be exponential minus 2 cr, and then you have minus h cross square divided by 2 mu c square minus 2c divided by r minus c square by r square dr. Okay, and so 4 pi and pi will go, and you will have 4c cube, then minus h cross square divided by 2 mu c square minus 2c divided by r minus c square by r exponential minus 2cr r square dr. So it's the same thing, rest of the thing is same. Now what you can do, you can bring those quantity, those terms where this r is not present. So what you bring, minus h cross square c square 2 mu, r is not present. So what you will do, you will differentiate r square exponential minus 2cr dr. Okay. Then again, what you will do, you will multiply this with this one. So h cross square divided by 2 mu will be there, and you will have 1 by r multiplied by r square will be r. For this term, it will be from this term. If you apply 1 by r multiplied by r square will be r exponential minus 2cr dr. Okay. Then for this term, what you have, minus e square, because for this you don't multiply with minus h cross square divided by 2 mu. So you multiply e square, and then again 1 by r multiplied by r square will give you r. So two different kinds of integral you have. One is 0 to infinity r exponential minus 2cr dr, and another is r square exponential minus 2cr dr. And for both these we can use the standard integral value. So the standard integral value is this one. Using the standard integral for r square exponential minus 2cr dr is this one, 1 by 4 c cube, and for r exponential minus 2cr dr 1 by 4 c square. So if you put these values of the integral, this integral value, this integral value, and this integral value, and finally you solve this equation, you simplify this equation by simple multiplication and simple algebra, which I will not talk about, that you can see yourself. It's all the steps is given. So the energy comes out to be h cross s square c s square divided by 2 mu minus c e s square. This is what you get, energy. Now you have got an energy. You see, I said you in the basic premise of the variation method is that when you get a trial function and when you guess a trial function, then trial function is dependent on a function which is called variation parameter, and here the trial function which I have guessed is exponential minus CR. So this C is the variation parameter, and I said you that when you find out the expectation value of the energy, that energy is also the function of C. So here you see the average energy or the expectation value of the energy which we have obtained is a function of C, h cross s square c s square divided by 2 mu minus c e square. Okay. So for obtaining the value of C, what we do? We minimize the energy, and for that, in order to find out the minima, what you do? You differentiate. So differentiate energy with respect to C and equate it to 0. And any C value corresponding to this equation will be for the minimum value of the energy. So what you do? You differentiate minus h cross s square c square divided by 2 mu minus c square. What does it mean? It means minus h cross square divided by 2 mu d divided by dc into c square minus c square, and c square will be 2c. So finally you will get h cross square c divided by mu minus c square is equal to 0, or c will be equal to mu e square divided by h cross square. So this is the value of variation parameter. And this is for the minimum eigenvalue, because we have differentiated the energy with respect to C and equated it to 0 for the minima of the energy. That will certainly be greater than the ground state wave function. That you always remember. That should be, if it is a trial function, that should be always greater than the trial ground state energy, if it is a trial function. Inserting this value C in the energy equation, what do you get? Energy which we have obtained is this one, h cross s square c square divided by 2 mu minus c square. This is your eigenvalue which we have got. Now what we do, you insert the value of C which you have obtained for the minima, mu e square by h cross s square, and see what energy you get. So this is your mu e square divided by h cross s square. It was, so mu square e raised to the power 4 divided by h cross s square minus mu e square divided by h cross s square into e square. So this is your C and this is your C square. Okay. So this value we can write, and then if you solve this one, what do you get? The energy which you get is minus 2 mu pi square mu e raised to the power 4 divided by h square. Okay. Now surprisingly, what you get here is the same energy which you obtain for the hydrogen atom. Okay, it's the same energy, for ground state hydrogen atom. The energy equation is 2 pi square mu e raised to the power 4 divided by n square h square. And for ground state, your n principal quantum number n is equal to 1. So the energy for the ground state comes out to be minus 2 pi square mu e raised to the power 4 divided by h square. Okay. So it's the same energy expression which we obtain. Okay. So why did we obtain the same relation? I said you that always the energy which you obtain from a trial function is greater than the ground state energy. But here it is not taking place. Here what the energy which we have obtained is the same ground state energy which we obtained in case of hydrogen atom solution also, for analytical solution of the hydrogen atom also. Why did it happen? It happened because the trial function which we have taken is actually the trial function, is the actual eigenfunction which we obtained from the analytical solution of the Schrodinger wave equation. You remember what we obtained from the Schrodinger wave equation? We obtained exponential minus r divided by a naught. Okay. But this is the trial function. This is the actual eigenfunction obtained from a constant will be there for 1s orbital. What do you get? The trial function psi 1 0 0 is like this one, a constant multiplied by exponential minus r divided by a naught. And what we have taken the trial function we have taken exponential minus cr. So both are same except this, the c is equal to 1 by a naught, which is a constant. Okay. If you put 1 by a naught is equal to c, then it's the same function. So same function we have taken as the trial function, and we have tried to confirm the basic premise of the approximation methods, that whether the variation method is actually suitable or not. And you find that if you take the same function as the trial function, which is obtained from the analytical solution of the Schrodinger wave equation, then you can get the same relationship of energy also. Now if you change your trial function, then it will give you another value. Now what does it mean? If you look at this one, I said you that the trial function c is equal to 1 by a naught. If you find the value of c, we have already find it is mu e square divided by h cross square. So do some, what is the classical expression of the Bohr's radius? A naught is equal to h square divided by 4 pi mu e square, or for the ground state, a naught for ground state. Of course, a naught is the ground state energy 0.529. Otherwise it would have been n square also. Okay, so it is ground state energy is ground state Bohr's radius is h square divided by 4 pi mu e square. So 1 by a naught, if you write, what do you get? You get 4 pi mu e square divided by h cross square. So, and what you can write, 4 pi h square, okay, this you can write as h cross square. So it is mu e square h cross square, and this is what the c value which you obtain. So the trial function which you have written as exponential minus cr is actually exponential minus r divided by a naught, and this is your exponential minus r divided by a naught. So this is your actual function obtained from the solution of the analytical solution of the Schrodinger wave equation, and this was your trial function. Both are same, so we get the same energy of the hydrogen atom. Okay. If you put the value of this energy and the this c value and the normalization constant in the normalized trial function, what do you get? The normalized trial function was c3 divided by pi raised to the power 1 by 2 exponential minus cr. And if you put the value of c, what do you get? You get 1 by pi a naught to the power 3 whole raised to the power 1 by 2 under root and exponential minus r divided by. And this indeed is the eigenfunction of the hydrogen atom, which we obtain when we apply Schrodinger wave equation to the hydrogen atom. So instead of applying Schrodinger wave equation for the hydrogen atom, what we did, we used the variation treatment and we guessed a trial function, and we got the same energy value as we obtained from the analytical solution of the Schrodinger wave equation. Okay, it means this is one of the good method of finding out the energy and the eigenfunction, eigenvalue and the eigenfunction of those systems for which analytical solution is not feasible. Now what we'll do, this was an example where we have taken the trial function as the same function which we obtained from the solution of Schrodinger wave equation. What you can do, you can change a trial function and again apply the same principle, variation treatment, and see what kind of energy you obtain. So another example of the same hydrogen atom I am taking, and now I am taking psi is equal to exponential minus alpha r square. Now you see this is different. This is not the same function. Okay, because what I have written is exponential minus alpha r square. Okay, so what you can do, you can apply the same variation treatment, and for that what you do, you find the Rayleigh ratio, and Rayleigh ratio has two parts, numerator and denominator. So you can calculate the numerator and you can calculate the denominator. And same will be the Hamiltonian, because it's hydrogen atom. Same principle will be there because del square will be only r dependent. So del square will be 1 by r square, del by del r square d by dr. Because you do not have theta and phi function, because theta and phi does not influence the energy of hydrogen atom. And in variation treatment, always what we do, we guess a trial function, we find out the energy. So we do not complicate the things. We remove theta and phi, and we write only the Laplacian as r dependent Laplacian converting to polar coordinates. Okay. So 1 by r square del by del r square del by dr we will use for del square, and the Hamiltonian will be minus h cos square divided by 2m del square plus e square by r minus e square by r. Okay. So if you use this one and you try to find out the numerator, okay, then again here you see I have found the del square value, del square psi value, and del square psi value comes out to be, if you do this calculation, you will come to 4 alpha square r square minus 6 alpha exponential minus alpha square. This I knowingly did not do. You can do it yourself. Okay. So from this to this we obtain del square phi, and now your numerator is psi h psi d tau. So psi is exponential minus alpha r square, h is minus, this is your psi, this is your h, minus h cross square divided by 2m 1 by r square d by dr, r square d by dr, exponential minus alpha r square minus e square by r exponential minus alpha r square 4 pi r square dr. The same thing which we did earlier. Okay. Now this was known to you. Del square psi is known to you. So this equation from 1 by r square d by dr to this one is equal to 4 alpha square r square minus 6 alpha exponential minus alpha r square. Okay. So minus e square by r exponential minus alpha r square, this equation remains same. Okay. If you do this, then if you multiply 4 pi r square, 4 pi you can bring this side, and r square you can multiply, and you can use the similar terms on the one side. Then you get three different integral: r raised to the power 4 exponential minus 2 alpha r square exponential minus 2 alpha square, and r exponential minus 2 alpha r square dr, and all integrated from 0 to infinity. Okay. These are very simple and every step is written. So if you again, for doing these integrals, what we use a standard integral table. And if you use a standard integral table, what you find is that these are the standard integral values: 3 divided by 32 alpha square, pi divided by 2 alpha under root, and then 1 by 8 alpha under root pi divided by 2 alpha, and 1 by 4 alpha. If you use this, then we can find the numerator, and the numerator is equal to this one. Okay. Having found the numerator value, one can find the denominator value. Now here, in the previous case, what we did, we normalized the wave functions, and then we said that denominator calculation is not required because it will be equal to 1. But here we did not normalize it. Instead, we find out the value of denominator. So denominator will be exponential minus 2 alpha r square 4 pi r square dr, and so the value will be 4 pi will be outside. So the value will be integral of this integral r square exponential minus 2 alpha r square dr, and this integral value is already there on this side. R square exponential minus 2 alpha is equal to this one. Okay. So this multiplied by 4 pi, the only thing is 4 pi multiplied by the value of the integral. Okay. So you have the numerator calculated, you have the denominator calculated, and you can find out the energy value. So energy value comes out to be 3h cross square alpha divided by 2m minus 2e square 2 alpha divided by pi raised to the power 1 by 2. This is the energy value. Now you see your trial function was exponential minus alpha r square. So what is the variation parameter here? The variation parameter here is alpha. So the value of alpha you have to find out. And for that, what you do? You differentiate with respect to alpha and equate it to 0, this energy value. And what do you get? The alpha value comes out to be simple differentiation. We are not going to explain every step. It's very obvious. All step is written. So alpha comes out to be 8 m square e raised to the power 4 9 pi h cross raised to the power 4. This is the value of alpha. Okay. So this value of alpha will correspond to the minimum possible value of energy from the trial function exponential minus alpha r square. Okay. Got this one? So using the calculated value of alpha is this one, 8 m square e raised to the power 9 pi h cross square if you use this one, then what is the energy value? If you put the alpha value here, you see all alpha value is in red written in 8 m square e raised to the power 4 divided by 9 pi h cross square. You have 3 here, you have 2 here, so it will be 4 by 3. Okay, and then you have here also you have alpha. So this alpha value multiplied by 2 multiplied by 8 will be 16. Okay, and finally what you get is the energy value, which you get is this one, minus 4 by 3 m e raised to the power 4 pi h cross square, or minus 0.4246 me4 divided by h cross square. Okay, so what is the exact energy? Exact energy is 4 pi square m e raised to the power divided by 2h square, and so the exact energy is minus 0.5 me4 divided by h cross square. If you go back to this function, what do you get? 2 pi square mu e raised to the power 4 divided by h cross square. So here also you have, it will be 2 pi square mu, instead of m I should have written mu, so you can correct that. All m should be mu because we are talking about hydrogen atom, or you can write the m also because it's the only one electron. So m e raised to the power 4 divided by 2h cross square. So the value is actually 0.5 me4 divided by h cross square. See how close we are to the actual value, but always whatever value you get from the energy from a trial function should be greater than the ground state energy, and this you see here. The ground state energy is minus 0.5 m e raised to the power 4 divided by h square, and the value which you obtain from the trial function is minus 0.4246 m e raised to the power 4 divided by h cross square. So from the two trial functions, phi is equal to exponential minus cr and phi is equal to exponential minus alpha r square, we have seen that this gives you energy exactly equal to the value of energy which we obtain by the solution of the Schrodinger wave equation. But this does not give the same energy because this is a trial function. This was the actual function, so it gives the exact energy. This is a different function, so it gives an energy very close to the actual value, but not the actual ground state energy. It's a minus 0.4246 me4 divided by h cross square. Got it? So we see that in approximation methods, in variation treatment, even the trial function, with the help of trial function, we can reach very close to the ground state energy, and so we can reach very close to the ground state eigenfunction also. So both eigenfunctions and eigenvalue for those systems for which analytical solution of the Schrodinger wave equation is not feasible can be obtained by using a variation treatment. These are very simple systems for hydrogen atoms. We can apply this to other systems also for which we already know the solution. And one system which we will do now will be the particle in a one-dimensional box. But for the time being, I stop here. We will do it in the next module. Okay, thank you.